Okay, last part for chapter number 2. Okay, so there are other gas equation of state that we will discuss in this part. Okay, so actually when we discuss about the other gas equation of state, actually this will involve different kind of relationship, and probably this relationship will be considered as the improved relationship compared to the basic ideal gas equation that we have learned before, okay, which is PVMRT or PVRT. Okay, first we have van der Waals equation, where for van der Waals equation, if you compare to the basic ideal gas relationship, so van der Waals equation will consider the intermolecular attraction force and also volume occupied by the molecules. So he introduced a new gas equation of state, where P plus A divided by V square multiplied by V minus B equal to RT, where A equal to 27 multiplied by gas constant R square multiplied by critical temperature square divided by 64 multiplied by critical pressure, and B is equal to gas constant R multiplied by critical temperature divided by 8 multiplied by critical pressure. Okay, where TCR equal to critical temperature and PCR equal to critical pressure. So we will have different gas equation of state introduced by van der Waals if you compare to the basic other gas of state equation. Okay, the second equation for the gas is the Betti-Bridgeman equation. So this equation include an equation based on 5 experimental determined constants. So Betti-Bridgeman conduct an experiment and get what I call 5 different constants that are already known for a specific gas, in order to include in their equation. So we have for Betti-Bridgeman equations, we have P equal to RU, universal gas constant, multiplied by T, temperature, divided by V bar square multiplied by 1 minus C divided by V bar multiplied by temperature power of 3 multiplied by V bar plus B minus A divided by V bar square, where A equal to A naught multiplied by 1 minus A divided by V bar, and B equal to B naught multiplied by 1 minus B divided by V bar. Okay, so the pressure P is in kilopascal, V bar actually specific volume, but now in meter cubic per kilomole, T in Kelvin, RU in kilopascal meter cubic per kilomole Kelvin. A, B, C, A naught and also B naught actually refer to the 5 experimentally determined constant, which is we can determine from the table for the Betti-Bridgeman equation. So this is the example for Betti-Bridgeman constant tables. So we have this one just example because we have other gas for the for this table, but here I just put 5 different gases for the Betti-Bridgeman constant. So we have here in the table, we have the value for A naught, A, B naught, B, and also C for different gases such as air, argon, carbon dioxide, nitrogen, and also hydrogen. Okay, so you need to use all these constant in order to apply the gas constant equation of state that introduced by Betti-Bridgeman equation. Okay, the third equation is from Benedict-Webb-Rubin. So we call Benedict-Webb-Rubin equation. And this equation actually extends the Betti-Bridgeman equation by raising the number of constants to 8. So for Betti-Bridgeman, they only use 5 constants, but for the Benedict-Webb-Rubin equation, they will use 8 constants. Okay, 8 constants. So we will have longer equation as shown here, where we have P equal to RU multiplied by T divided by V bar plus bracket B naught multiplied by RU multiplied by T minus A naught minus C naught divided by T square multiplied by 1 divided by V bar square plus B small letter multiplied by RU multiplied by T minus A divided by V bar cubic plus A multiplied by alpha divided by V bar power of 6 plus C divided by V bar power of 3 multiplied by temperature square multiplied by 1 plus gamma divided by V bar square multiplied by exponent power of negative gamma divided by V bar square. So this is the equation for Benedict-Webb-Rubin equation. So P in kilopascal, V bar in meter cubic per kilomole per kilomole T in Kelvin, RU in kilopascal meter cubic per kilomole Kelvin, and the value of A, B, C, A naught, B naught, C naught, alpha and gamma is the 8 constant that used by the Benedict-Webb-Rubin equation, and this 8 constant can get from the specific table for Benedict-Webb-Rubin equation. So this is just an example. So I just provide few guesses for the Benedict-Webb-Rubin equation constant. Okay, so we have gas for the nitrogen, carbon dioxide, and also carbon monoxide. So this is the table for Benedict-Webb-Rubin equation constant table. And the last one we have virial equation. So this is quite long actually. So we have P equal to RT divided by V plus A function of T divided by V square BT, okay, divided by V cubic plus C divided by V power of 4 plus G dt divided by V power of 5 and so on. So A, B, C, D is considered as virial coefficient, and A are the function of temperature. So we need to, in order to use this equation, we need to know what is the function of A, B, C, and also D, and so on. So these are 4 different gas equation of state, other than the basic ideal gas equation of state. Example 3.10, predict the pressure of nitrogen gas at T equal to 175 Kelvin and specific volume equal to 0.00375 meter cubic per kg on the basis of A, the ideal gas equation, B, the van der Waals equation, C, the Betti-Bridgeman equation, and D, the Benedict-Webb-Rubin equation. Compare the value obtained to the experimentally determined value of 10,000 kilopascal. Okay, so we need to compare all the pressure that are obtained by using different ideal gas equation, compare with the pressure that obtained from the experimental approach, which is 10,000 kilopascal. Okay, so data given: substance is nitrogen gas, the temperature given T equal to 175 Kelvin, specific volume V equal to 0.00375 meter cubic per kg, and P actual from the experimental approach is equal to 10,000 kilopascal. Okay, first determine the nitrogen gas pressure through ideal gas equation. So we have PVRT formula. So now we implement a PVRT for the nitrogen gas and 2. So we need to determine P and 2. So we already know that P and 2 equal to 0.00375 meter cubic per kg, and R and 2. So we need to find the value for the gas constant value for nitrogen. So we have, normally we can get from the table in the textbooks or normally given. Okay, so if the question doesn't give you the table to determine the gas constant for the nitrogen, normally the value of gas constant for nitrogen normally given in the question. So R gas constant for nitrogen equal to 0.2968 kilopascal meter cubic per kilogram Kelvin, and T and 2 the temperature for the nitrogen gas equal to 175 Kelvin. So rearrange the ideal gas equation for the nitrogen. So we have P and 2 pressure for nitrogen equal to gas constant for nitrogen multiplied by temperature for the nitrogen divided by specific volume for the nitrogen gas. So just substitute all the value that we have. So the pressure for the nitrogen gas is 13850.67 kilopascal. Okay. So now compare with what I call the value, the actual value of the nitrogen pressure based on the experiment. Okay, by using the error percentage equation. So we have error percentage to P ideal minus P actual divided by P actual multiplied by 100. So substitute the value of P that we obtain by using the ideal gas equation and also the actual one. So we'll get the error is around 38.5%. So the error quite high. Okay, done. Question A. Question B. Determine the nitrogen gas pressure through van der Waals equation. Okay, so from the critical point table for the nitrogen, so we can get this value from the table that provided in thermodynamic textbook, any thermodynamic textbooks. So we'll have the critical temperature for nitrogen is equal to 126.2 Kelvin, and the critical pressure for nitrogen gas equal to 3.39 megapascal. So based on the what I call van der Waals equation, so we need to determine what I call the value of A. So A equal to 27 multiplied by R for the nitrogen square multiplied by critical temperature square divided by 64 multiplied by critical pressure. So substitute all the data that we have. So we'll get the value of A equal to 0.1745 meter power of 6 kilopascal divided by kilogram square, and B equal to R for the nitrogen gas multiplied by critical temperature divided by 8 multiplied by critical pressure. So substitute the value. So we will get B equal to 0.001381 meter cubic per kg. Okay, so take the what I call the equation for van der Waals, where P nitrogen plus A divided by V nitrogen square multiplied by V nitrogen minus B equal to a gas constant for nitrogen multiplied by the temperature for the nitrogen gas. So rearrange the equation because we want to determine the pressure of the nitrogen gas based on the van der Waals equation. So P nitrogen equal to R nitrogen multiplied by temperature of the nitrogen divided by V nitrogen minus B minus bracket A divided by V nitrogen square. Okay, substitute the value, all the value that we have. So we'll get nitrogen gas pressure is equal to 9515.67 kilopascal, and then compare with the actual pressure for the nitrogen gas by calculating the error percentage. So you'll get the error by using the van der Waals equation is 4.84%, less than 5%. So in comparison, the van der Waals equation is more accurate compared to the ideal gas, the basic ideal gas equation. Okay, next C, determine the pressure gas and nitrogen gas pressure by using Beatty-Bridgeman equation. Okay, so we know that what I call the V bar, actually the specific volume in kilomole unit. So V bar, in order to get the V bar value, so we need to multiply the specific volume that we have with the molar mass M, capital letter, for the nitrogen. Okay, so we need to refer to the molar mass for the nitrogen gas, which is equal to 28.013 kilogram per kilomole, multiply with the specific volume for the nitrogen gas. So we need to multiply with 0.00375 meter cubic per kg. So we will get the value for the V bar for the nitrogen, which is 0.10505 meter cubic per kilomole. Okay, specific volume in meter cubic per kilomole equal to V bar. Okay, refer to the Beatty-Bridgeman constant table for nitrogen, because in the Beatty-Bridgeman equation we have 5 different constant. So this constant value you need to refer to the Beatty-Bridgeman constant table, refer to the nitrogen gas. Okay, we have here all the constant, 5 constant that involved with Beatty-Bridgeman constant. Okay, first we need to determine the value of A equal to A naught 1 minus A divided by V bar. So substitute equation, substitute the value, so we will have A capital letter equal to 102.29, and for B equal to B naught 1 minus B divided by V bar and 2 for the nitrogen. Substitute the equation, so we will have B capital letter in terms of constant value equal to 0.0538. Okay, and then substitute the value for A, B, and also C into the equation of the Beatty-Bridgeman equation. Okay, as shown in this slide. Okay, substitute the value. The other things is you need to know the value of Ru, where the value of Ru is constant, universal gas constant, which is equal to 8.314 kilopascal meter cubic per kilomole Kelvin. And substitute the value in the equation for the Beatty-Bridgeman equation. So we get the value of nitrogen gas pressure by using this method, or this equation is 10110 kilopascal. Calculate the error percentage in order to make comparison with the actual one. Okay, 10110 minus 10,000 kilopascal divided by 10,000 kilopascal. So we'll have the error percentage is 1.1%, which is less than compared to the previous method or previous equation of van der Waals equation. Okay, which means Beatty-Bridgeman equation more accurate compared to van der Waals equation. The last equation, where we need to determine the nitrogen gas pressure through Benedict-Webb-Rubin equation. Okay, so this is the equation for Benedict-Webb-Rubin equation. So we need to determine all the 8 parameters or 8 constant by using the table before we calculate the pressure for the nitrogen gas by using the Benedict-Webb-Rubin equation. Okay, refer to the Benedict-Webb-Rubin constant table for nitrogen here. So we have all 8 constant value for nitrogen gas. So we need to use this and substitute into the equation, where Ru equal to 8.314 kilopascal meter cubic per kilomole Kelvin. Okay, substitute into the equation. So we'll have the pressure of the nitrogen gas by using Benedict-Webb-Rubin equation equal to 10009 kilopascal. Calculate the error percentage. So we'll get 0.09%, which means this Benedict-Webb-Rubin equation more accurate compared to the Beatty-Bridgeman equation. Okay, so Benedict-Webb-Rubin equation is the most accurate compared to others, with only 0.09% error if you compare with the actual pressure that obtained through the experiment. Okay, I think that's all for this chapter. Okay, so end of chapter number 2. That's all. So get prepared for your tutorial for chapter number 2. So the important thing for this chapter, actually, you need to know how to use the table, properties table, and also for the gas, you need to know how to use the equation that involved for the ideal gas. Okay, that's all. Assalamualaikum.